Hello dear students, let us continue our discussion on the topology of the real number system, which is the second unit of your course. So I have already discussed about open sets in class and some of their properties. I have discussed about epsilon neighborhood. So just let me recall this concept. Epsilon neighborhood of a point. Right, let x belongs to real number. X is a real number and you take epsilon greater than 0. Okay, then the open interval is x minus epsilon to x plus epsilon, okay, is called an epsilon neighborhood of the point x. Okay, say in diagram you can say, so if x is some point here and you take this x minus epsilon to x plus epsilon, so that is you keep x as center and take this distance equal to epsilon. Okay, this distance also equal to epsilon, but in the left direction. Okay, this was towards right, this was towards the left. Okay, so the open interval that you get, that is a neighborhood of the point x. Okay, so you change the value of epsilon, you get different neighborhoods. Okay, you take a smaller epsilon, you will get a smaller interval. You take a larger epsilon, you will get a larger interval. Okay, that is the thing. Say for example another one, I can take something like 1 and take epsilon equal to 2, then 1 minus 2 is minus 1, 1 plus 2 is 3. So minus 1, 3 is a neighborhood of epsilon neighborhood of 1, where epsilon is taken as 2. If I take epsilon equal to say 0.5, in that case you will have say 0.5 and 1.5 somewhere here, right? So there is also an epsilon neighborhood of a point, right? So with this concept we can define something called limit point of a set. Limit point of a set. Okay, so another name for limit point is also cluster point or accumulation point. Okay, so usually it's called limit point. So a point small x inside the set of real numbers is a limit point of subset A of R if every epsilon neighborhood of x contains at least one point of capital A different from x, different from the point x itself. Okay, so note that the point x need not be a point inside A. Okay, note that x need not be inside the set A. Okay, so limit point of a set may not be a point inside the set. Okay, right. So what does it say is actually x will be called a limit point of the set, say capital A, if whatever epsilon neighborhood you take. Okay, maybe large, maybe small. Okay, whatever, all possible epsilon neighborhood you take, this type of neighborhoods, whatever you take, always you will be able to find at least one point of the set capital A different from x. Okay, suppose x is inside A, so every epsilon neighborhood will contain x, that's not a problem. Okay, but we need something other than x. Okay, if that is possible, then we say that x is the limit point of A. Okay, otherwise it's not possible. otherwise it's not a limit point. So if every epsilon neighborhood contains at least one point of A different from X, then we'll say that X is a limit point. So X is not a limit point if the negation is true. Okay, what is the negation? Every will be replaced by there exist. So there exists a neighborhood of X that doesn't contain any point of A, okay, different from X. Right, that will give us the definition of not a limit point. Okay, so we'll write it that way also. So X belongs to R is not a limit point, not a limit point of capital A if there exists an epsilon neighborhood of capital A that doesn't contain any point of A, different from X, okay, right? So that's the thing. So for example, let's say 1 is not a limit point of this set, say the set A equal to 0, 2. Okay, I have taken a simple finite set having only 2 elements, and I'll try to show that 1 is not a limit point of this set. Okay, so the set A consists of only these 2 points, okay, 0 and 2. So 1 is not a limit point. Okay, so for that, what I need to show, that there is an epsilon neighborhood of epsilon neighborhood of X, right? Yeah, so there is an epsilon neighborhood of 1 that does not contain 0 also, that does not contain 2 also. Okay, so can we find some neighborhood? So from this diagram, by geometrical idea, you can easily find out. This is what 0.5, this is say 1.5. okay, if I take this open interval around 1, it doesn't contain 0 also, doesn't contain 2 also, right? So that means 1 is not a limit point. We could find a epsilon neighborhood which does not contain any point of A. Okay, so 1 is not a limit point. So let us check whether 0 is a limit point or not. 0 is not a limit point. Limit point of the set A equal to 0, 2. It's not a limit point of this set. Why? You take this is the point, say 0, this is the point 2. Okay, we can find a neighborhood around 0. Okay, say this is minus 0.5 to 0.5. So this neighborhood contains only the point 0 of the set A. It doesn't contain the other point. Okay, so this neighborhood contains no point of capital A other than 0. Okay, so minus 0.5 comma 0.5 is an epsilon neighborhood. Okay, epsilon neighborhood of 0 that doesn't contain any points of capital A other than, so it contains at least one point of capital A, but that is 0 itself. So 0 cannot be a limit point, okay, other than 0, right? So 0 is not a limit point of this set. Similarly, we can show that 2 is not a limit point. Okay? We can take some interval of this type, say 1.8 to 2.2, right? That way also we can take. That interval will not contain the point 0. It will contain only the point 2. Okay, so it's not a limit point. So in fact, we will show that a finite set has no limit points. Okay? What about the set phi? If phi is equal to phi, what are the limit points? So you see from the definition itself, it follows that the empty set cannot have limit points. right? Because a point will be called a limit point if you can find, if for every epsilon neighborhood of that point you can find at least one point from the set A. So if A is itself phi, you cannot find such a point. So phi has no limit points. Okay, then phi has no limit points. No limit points. Okay, so we have some definition like this: derived set. What is a derived set? Derived set is the set of all limit points. Set of all limit points. Limit points of one set A subset of R is called the derived set of A. Is called the derived set of A. Okay, it is denoted by dA, or many times A dash. Okay, so dA is more common. We will use dA. Okay, we will use the notation dA. So what is derived set of phi? Just now we've seen phi has no limit points, so derived set of phi is phi only. Okay, there are no limit points. So in fact we will do this result that every or a finite set has no limit points. Finite set has no limit points. Limit points. Okay, or other way we can say that if A is finite, then derived set of A is empty. Okay, it has no limit points. So how to show that? Basically we will use the geometrical idea here. Okay, suppose you have a finite set. In your first unit we have seen the finite sets can be written in this way: A1, A2, A3, A4, A5. okay, like that, something like this. So what we do is we try to check whether a given number x is a limit point or not. Okay, so for that what I do, I find out the distance of x from each of these points. Okay, distance between x and A2, distance between x and A1. Okay, distance between say x and A4. Then I find out distance between x and A5. Okay, and then I'll take the minimum of all these distances. After taking the minimum of all these distances, say from here maybe the minimum is this, I construct an open neighborhood, that is epsilon neighborhood of x, and I'll show that that epsilon neighborhood will not contain any other point of A different from x. Okay, so that is the basic idea. So let us see how to go about with the proof. So let A equal to set of A1, A2, A3 up to AN be a finite set. Okay, we want to show that it does not have any limit points, right? So let x belongs to real number, be any point. Okay, so we will show that no real number can be a limit point of this set. Okay, let x belongs to R be any limit point. So it may happen that x belongs to capital A itself. If x belongs to capital A, then x will be like something like x is equal to say AJ for some j equal to 1, 2 up to n. Okay, if x is in A, then x is of the form AJ for some j equal to 1, 2 up to n. Okay, so we take epsilon equal to, so we measure the distance of the other elements from the element AJ. Okay, so we take epsilon equal to minimum of these distances, mod of say AJ minus AI, mod of AJ minus AI, such that I goes from 1 to up to n and I is not equal to j. Okay, so all these distances are positive distances. Okay, but so if we take this say epsilon neighborhood of AJ minus epsilon to aj plus epsilon. That neighborhood will not contain any of these points ai. Okay. Then mod of aj minus ai, this is always greater than or equal to epsilon, right? Mod of aj minus ai, this is always greater than or equal to epsilon, because epsilon is the minimum of this collection. Okay, so each element of this collection will be greater than or equal to epsilon. So for all I equal to 1 to up to n and I not equal to j. Okay, so this implies ai does not belong to this interval aj minus epsilon to aj plus epsilon. Okay, because if it belongs to this interval, then mod of aj minus ai, this has to be less than epsilon. Okay, if it belongs to this interval, then modulus of aj minus ai, that has to be less than epsilon, right? Okay, you see the definition of this epsilon neighborhood. Open interval x minus epsilon to epsilon is called open interval, is called an epsilon neighborhood. So if y belongs to this neighborhood, then what is the relation between modulus of xy, x minus y and epsilon? So if y belongs to this, then x minus epsilon is less than y less than x plus epsilon. Okay, so we bring x to the other side, so minus epsilon less than y minus x less than epsilon. Okay, so that means actually mod of y minus x is less than epsilon, right? So from there, so since here aj minus ai modulus is greater than or equal to epsilon, that means none of the ai's can be there in this epsilon neighborhood. Okay, so the epsilon neighborhood aj minus epsilon to aj plus epsilon of aj contains no point of capital A different from aj. Okay, that means, so therefore aj is not a limit point. Okay, we have been able to produce a epsilon neighborhood which does not contain any other point of a. Okay, so aj is not a limit point. Okay, similarly, if x doesn't belong to a, if x does not belong to a, then let us take then x is not equal to ai. No? X is not equal to ai for all I 1 to up to n, right? So let epsilon equal to minimum of mod of x minus ai. So I am collecting the distances from x to ai, such that I goes from 1 to up to n. Okay, then epsilon is greater than 0. Epsilon is greater than 0 because x is not equal to ai. Oh, sorry, I forgot to write here also. Just add this part, then epsilon is greater than 0, right? Okay, so here also epsilon is greater than 0, and mod of x minus ai, this is always greater than or equal to epsilon by definition. Epsilon is the minimum of all these values, so each of these values will be greater than or equal to epsilon for all I equal to 1 to up to n. That means what? ai does not belong to x minus epsilon to x plus epsilon. Okay, for all I equal to 1 to up to n, right? So that means what? So the epsilon neighborhood x minus epsilon to x plus epsilon, okay, of x contains no point of capital E. Okay, so therefore x is not a limit point. We have got an epsilon neighborhood which doesn't contain any point of capital A, so x is not a limit point of capital A. Okay, so that is the thing. So that means whatever real number you take, that real number cannot be a limit point of the finite set A. So therefore A has no limit points. no limit points. Limit points. Okay, so derived set of a finite set is always empty. Okay. So let us have a look at some other standard sets which do not have limit points. Okay, so for exercise, say derived set of the set of natural numbers is phi. Okay, the set of natural number doesn't have any limit point. Okay, so how will you show that? So it's quite simple. So let yeah. So no real number can be a limit point of the set of natural numbers. Okay. So we can take first let us show that no natural number can be a limit point of the set of natural numbers. Okay. So let n belongs to natural number, then the epsilon neighborhood. So what is the most obvious epsilon neighborhood that we can take is this n minus half to n plus half. Okay, you have the set of natural numbers, right? So in the set of natural number you have say n plus 1, okay, n minus 1. So distance between two natural numbers is always 1. Two consecutive natural numbers is 1. So you take half of that, subtract n minus half to n plus half. So this interval will contain only the natural number n. It will not contain any other natural number. Okay, so then the epsilon neighborhood n minus half to n plus half contains no point of capital N other than n itself. Okay, so n is not a limit point. So no natural number can be a limit point of the set of natural number. Okay. Now suppose that x is not a real number which may not be natural, then how to show that it's not a limit point. Okay. So we have a result that if x is a real number, then there always exist two natural numbers between which it lies. Okay. So yeah, so if that real number is negative, okay, then we need to separate that case. Okay. So if it is a negative real number, we can easily separate that case, right? So say if let x belongs to real number and x doesn't belong to the set of natural number. Okay. So if x is less than 0, so if x is negative, in that case can you find an open interval which does not contain any natural number. Okay. So say x is somewhere here, 0 is somewhere here, and these are 1, 2, 3 like that. Okay. So then which interval can I take so that this becomes the interval, the epsilon neighborhood is such that it doesn't contain any natural numbers. Okay, so we can take the interval say x plus this distance by 2, okay, half of this distance, right? So then the epsilon neighborhood this one x minus what is this distance? It is modulus of x. This distance is modulus of x. So x minus mod x by 2 to x plus mod x by 2. Okay, this neighborhood does not contain because this will be a subset of the negative real numbers. Okay, doesn't contain any point of the set of natural numbers. Okay, so this if x is a negative real number, it cannot be a that is called limit point of the set of natural numbers. Okay, now if x is positive real number, okay, then what we can do? So in that case we can take the difference between these two values. Okay, any positive real number will lie between two natural numbers, okay, or two integers, right? If x is greater than 0, then there exists n belongs to natural number such that n minus 1 is less than or equal to x and strictly less than n. Okay, that means x lies between two consecutive integers. Okay, so the epsilon neighborhood, so we'll take an epsilon neighborhood which will so let epsilon equal to, so what we'll do, we will take half of this distance, right? X is somewhere here and this is the next natural natural number which is immediately below it, or integer which is immediately below it, and this is the integer which is immediately above this. So what we do is we take the length of this part and consider the minimum one. Okay, considering the minimum one, we will draw one open interval, so that will not contain any other points of the natural numbers. Okay, so let epsilon equal to minimum of mod of x minus n minus 1 comma mod of x minus n. Okay, then the epsilon neighborhood x minus epsilon to x plus epsilon does not contain, doesn't contain any natural number. Okay, contain any natural numbers. Okay, so no natural number can be a limit point of n, so therefore derived set of n is actually 5. Right, so that is the thing. Now can we do something about or can you see some examples where the limit point exists? Okay, till now we have, whatever we have seen, that there are no limit points, okay, in the examples. Well, now let us see some examples where there are limit points. Okay, so say for example this set show that. So in our first unit we have already done Archimedean property of real numbers. Okay, so we'll use this somewhere. Show that this set A equal to 1, 1 by 2, 1 by 3, okay, 1 by 4. So it is the collection of reciprocals of natural numbers, has limit point 0. Limit point 0. Okay. So we have to show that 0 is the limit point of this. Okay, so for that what I have to do, I have to show that every epsilon neighborhood of 0 contains at least one point from this set different from 0. Okay, so we have 0 doesn't belong to this set, 0 does not belong to A. Okay, so let epsilon greater than 0, then we consider the epsilon neighborhood, consider the epsilon neighborhood, 0 minus epsilon to 0 plus epsilon. Okay, so our aim is to find an element inside this set which belongs to this neighborhood. Okay, so by Archimedean property, there exists a natural number, right? There exists n belongs to natural number such that 1 by n, so epsilon is greater than 0, so given epsilon greater than 0, there exists a natural number such that 1 by n is strictly less than epsilon. Okay, so this means 1 by n is actually a member of minus epsilon to plus epsilon. Okay, since 1 by n is already greater than or equal to 0. So 1 by n is the number which lies between 0 and epsilon. Okay, so 1 by n belongs to this minus epsilon to plus epsilon. That means whatever epsilon you take, whatever epsilon neighborhood you take, we will always find a point inside the set A. Now this 1 by n is a point inside the set A because the set A contains the set of all reciprocals of natural numbers. So but 1 by n is an element of capital A. Okay, so every epsilon neighborhood of 0 contains at least one point of capital A different from 0. So 0 is a limit point. Therefore 0 is a limit point. Limit point of the set. Okay. So this was one example where we have limit points. Okay. Another exercise, if you see, if you observe nicely, is quite similar. Show that this, say the set 1 plus 1 by n such that n belongs to natural number. This set. Show that 1 is a limit point. 1 is a limit point of this set. Okay, how to show this? Okay, so let us try this. It's almost similar. So whether 1 is a member of this set, it's not a member of this set. Okay, if you take n equal to 1, it's 2. If you take n equal to 2, it's 1 plus half, that is 3 by 2. Okay, so like that. 1 is actually not a member of this set. If 1 is a member of this set, then 1 plus 1 by n will be equal to 1 for some n. That means 1 by n is 0 for some n, but that's not possible. Okay, if that happens, then 1 becomes equal to 0. So that means 1 is not an element of this set. So in the beginning itself, I had remarked that limit point of a set may not be an element inside the set. Okay, so this is another example where limit point is actually not inside the set. Okay. So now how to show that 1 is a limit point? So we'll take a epsilon neighborhood, right? Let epsilon greater than 0. Consider the epsilon neighborhood. So here also we will use the Archimedean property. Consider the epsilon neighborhood 1 minus epsilon to 1 plus epsilon. Okay, so by Archimedean property, there exists a natural number such that 1 by n is strictly less than epsilon. So what do I need? I need numbers of the type 1 plus 1 by n. So 1 plus 1 by n will be less than 1 plus epsilon. Okay, and also it is greater than or equal to 1. Also 1 plus 1 by n, this is always greater than or equal to 1, right? So therefore 1 plus 1 by n is an element inside 1 minus epsilon to 1 plus epsilon, and 1 plus 1 by n is also an element inside the set A. That means for every epsilon neighborhood, we are being able to produce one point inside the set A, okay, which belongs to that epsilon neighborhood. So that means therefore 1 is a limit point. Point of capital A. Okay, so that is the idea. Say show that 0 and 1, okay, are limit points of say open interval 0 1. Okay, so all of you know what is an open interval. Open interval 0 1, it is the set of all those real numbers which satisfy 0 less than x less than 1. Okay, this is the set of all real numbers lying between 0 and 1. Right, so we'll consider one epsilon neighborhood. So from the diagram itself, you can see that say 0 1. So your set is actually this part, all the numbers lying between 0 and 1. Okay, So if we take any epsilon neighborhood of 0, you will see the right part actually contains points which belong to this 0 1. Okay, right. So whatever epsilon neighborhood you take, it will always contain points which are greater than 0, right? So that's always a yeah. Okay, there is always a yeah. Sorry, what did I say? There is always a point. There is always a point inside the set 0 1 which is there in each epsilon neighborhood of 0. Okay, so how will you do it? Let epsilon greater than 0 be given. We consider the epsilon neighborhood. So here also this Archimedean property will be useful, or without Archimedean property also we can do it. Consider the epsilon neighborhood 0 minus epsilon to 0 plus epsilon. Okay, so remember here epsilon is any arbitrary this positive quantity. Okay, so it may happen that this epsilon is quite large, maybe something like this. Okay, so one way of doing is this, that I have taken an interval of 0 minus epsilon to 0 plus epsilon, and I take epsilon by 2, and I claim that epsilon by 2 is a point inside the set 0 1. Okay, but that may not happen always, because somebody may choose epsilon to be very large, say something like 4. In that case epsilon by 2 is not inside the set 0 1. Okay. So we have to think a little bit. So if what happens if epsilon is greater than or equal to 1? Okay, if epsilon is greater than or equal to 1, then there is a problem. Otherwise there is no problem. This is 0, this is 1. If I take some epsilon which is greater than or equal to 1, okay, in that case I need to find out some elements, okay, inside the set 0 1. And if epsilon is less than 1, then the finding out the elements is quite simple. Okay, in this case also it's simple, but we need to separate the two cases. Okay, so if epsilon is greater than or equal to 1, then so what I need to show is every epsilon neighborhood contains at least one point of the set capital A, that is 0 1. Then half belongs to 0 1. So if you take an interval of this type, say 0 plus epsilon, okay, so which element of this, which point of this set 0 1 satisfies that it is inside minus epsilon to plus epsilon? If you observe carefully, every point of the set 0 1 satisfies this property. Okay, so if epsilon is equal to 1, we can in particular we can take half, which is an element inside 0 1, and half is less than epsilon. Okay, so if epsilon is greater than or equal to 1, then half belongs to 0 1 satisfies half belongs to minus epsilon to plus epsilon also. Okay, and if epsilon is less than 1, in that case I cannot take half. Okay, because it may happen that somebody has taken epsilon smaller than half. Okay, so what should I take? I cannot take something like 1 by 100 also, because it may happen that the person has taken something which is less than 100. Okay, so in this case our choice of the point inside the set 0 1 will depend on the choice of epsilon. So if epsilon is less than 1, we take epsilon by 2, then epsilon by 2, this is a point inside 0 1. Okay, epsilon is less than 1, right? So epsilon by 2 is a point which is less than epsilon and which is also less than 1. So epsilon by 2 is a point inside 0 1, satisfies epsilon by 2 belongs to minus epsilon to plus epsilon. Okay, it belongs to this set also, because modulus of epsilon by 2 is strictly less than epsilon. Okay, as epsilon by 2 is strictly less than epsilon. Okay, 0 less than epsilon by 2 less than epsilon, right? So whatever epsilon we choose, we can always find some points inside the set 0 1 which belong to that particular interval, the epsilon neighborhood. Okay, so 0 is a limit point. Thus 0 is a limit point. Is a limit point of 0 1. Okay, so similarly for we can also show that 1 is a limit point, right? So let epsilon greater than 0, consider the neighborhood, neighborhood 1 minus epsilon to 1 plus epsilon. Okay, so here what is the problem? If we choose epsilon very large, it may happen that 1 minus epsilon goes beyond maybe somewhere here. Okay, so that cases we have to deal with. So if 1 minus epsilon is less than 0, okay, then what to do? Less than or equal to 0, then any point inside this will satisfy. Okay, and if 1 minus epsilon is greater than 0, okay, in that case what to do? Right, so if 1 minus epsilon is less than or equal to 0, then you just take any point here, say half belongs to 0 1, satisfies half belongs to 1 minus epsilon to 1 plus epsilon also. Okay, because 1 minus epsilon is already less than or equal to 0, right? And 1 minus half, right? Half is somewhere here, so 1 minus half, modulus of half minus 1, so that is equal to half, and that is always less than or equal to epsilon, right? Because epsilon is greater than or equal to 1. 1 minus epsilon is greater than or equal to 0. That means what? Epsilon is greater than or equal to 1. So half is always less than epsilon. Okay. So if our epsilon is something like 1 minus epsilon less than or equal to 0, then half belongs to this point, this set satisfies that half belongs to the interval 1 minus epsilon to 1 plus epsilon also. Okay, we just need to find one point which belongs to the epsilon neighborhood. Okay, so in this case the half will act as our point. Okay, and if 1 minus epsilon is greater than 0, that means epsilon is less than 1. Okay, then we can take this 1 minus epsilon is greater than 0, that means 1 minus epsilon is somewhere here. So we can take something like 1 minus epsilon by 2. It will be a point somewhere here, right? Then 1 minus epsilon by 2 is a point which is inside 0 1. Okay, because 1 minus epsilon by 2 in that case will be greater than 0 but less than 1. Okay, satisfies 1 minus epsilon by 2 belongs to 1 minus epsilon comma 1 plus epsilon. Okay, yes. Right, so all cases have been dealt with. Okay, 1 minus epsilon less than or equal to 0, 1 minus epsilon greater than 0. So in each of these cases we are able to find some point inside the set 0 1 which also belongs to the epsilon neighborhood. Okay, and in this case also we are able to find a point 1 minus epsilon by 2 inside 0 1 which also belongs to the same epsilon neighborhood. Okay, so therefore 1 is a limit point of the set 0 1. Okay, so in a similar way we can also show that A and B are limit points of this open interval AB. Okay, another exercise, A and B are limit points of closed interval AB. Okay, and that is also correct. The process of showing is the same. Okay, we need to find some point which lies inside a plus epsilon, a minus epsilon to a plus epsilon. Okay, so the system is similar. You take a plus epsilon, consider the interval a minus epsilon to a plus epsilon. Okay, so if a plus epsilon is greater than or equal to b, then you can take any point inside, say a plus b by 2, which belongs to the interval ab and also belongs to the neighborhood a minus epsilon to a plus epsilon. Okay? And if a plus epsilon is less than b, in that case we can take something like a plus epsilon by 2. So this will be a point which is less than a plus epsilon. Okay, so it will lie inside this, and it will also lie inside this set, inside the set AB. Okay, so that way we can manage. So I think you can try this at home, and we will discuss some more aspects in the next class.